In this video, we're going to be talking about spherical refracting surfaces. So the question we need to ask is, what is a spherical refracting surface? Well, a spherical refracting surface is a spherical boundary separating two different medians. What does that mean exactly? So suppose we have a sphere here made of glass, and inside of this glass we have an object. And we place this whole sphere inside of air. So out here is air. This boundary right here between the glass and the air is a spherical refracting surface, because the sphere has a different index of refraction than the air does. Air's index of refraction is 1. Glass can be in a range, but typically it's like 1.5. So, since these have different index of refractions, the light ray bends as it approaches. Let me do this different color. The light ray approaches the spherical surface, and then it bends in some path. Well, if you know anything about refracting surfaces, this is modeled by Snell's law, which is n1 sine theta equal to n2 sine theta. But this is for flat surfaces, flat refracting surfaces. So what they did was they wanted to make this whole problem simpler, so they did a bunch of geometry and algebra, and they made this equation more consistent for spherical surfaces, and this equation is as follows. We have n1 over dO plus n2 over di is equal to n2 minus n1 over plus or minus r. Now, a lot of variables here, but they're all pretty straightforward. N1 is the index of refraction of the first median. The first median being the material or the substance that the object starts in. N2 is the index of refraction of the second medium, or where the light ray exits. So in this case, our light ray starts at our object here, and then it travels to the spherical surface into air. So N2 would be air. dO, of course, is how far the object is in the first median, typically denoted by dO, or it could be S, depending on some textbooks. I write it as dO. And di is where the image appears relative to the surface. And the sign of di tells you a little bit about where the image is, but we'll look at that later. Now, r is the radius of curvature of the refracting surface. For a sphere, that radius is consistent around the whole sphere. Now, positive or negative, that just is telling you what does the light ray leaving the object see, or what kind of surface does it encounter. If we look at our problem here and bring it down, the light ray leaving our object encounters a concave surface. Concave surfaces give negative r values in our equation. Whereas, if we have something like this, where we have an object, we have a light ray that leaves it, the light ray encounters a convex surface. Convex surfaces give positive r values. Another way to think about this is if the center of curvature of the refracting surface is on the same side as the object, it's negative, or if it's on the opposite side of the object, it's positive. Right, because this radius, if we continue the circle, would be in the middle. Same is true here. If the center of the circular curvature is on the same side as the object, it's a negative value of r. If it's on the opposite side, it's a positive value for r. These are just a few things to keep in mind as we jump into our first problem. So for our first problem, we have a tiny defect is embedded inside a solid glass sphere of radius 20 centimeters. The defect is located 12 centimeters from the spherical surface. The index of refraction of the glass is 1.52. As seen from outside the sphere, or in air, where does the defect appear to be located relative to the surface? So, the first thing we want to do is we want to write our equation. We want to say n1 over dO plus n2 over di That's equal to N2 minus N1 over plus or minus R. Now, let's list out some of the things we know. Like we said earlier, N1 is the index of refraction of the first median, which is where the object is initially at. So in our problem here, the object is initially inside the glass. So N1 is equal to 1.52. Now, N2 is the index of refraction of the second median. So if we draw a little light ray here, light ray leaves, it encounters the surface that separates the glass and the air. So our second surface is air, which has an index of refraction of 1. So N2 is equal to 1. Now DO is how far the object is inside of that spherical refracting surface, or how far it is away from the spherical refracting surface. In this case, it's going to be 12 centimeters. DI is what we're looking for, so we don't know that. Now R, the radius is 20 centimeters, but we have to determine the sine of it. Like we said earlier, if we bring our surface down here, oh, that's a bad circle. Let me try that again. That's better. We have our defect here. The light leaving the defect encounters a concave surface. Like we said earlier, concave surfaces get negative R values, which means our radius is negative 20. We also said that if the center of curvature of the radius is on the same side as our object, it's negative. It's just another way to think about it. But given this information, we can determine that our R is going to be a negative value. So now that we have all of these values, we can plug them into our equation. That's what I'm going to do right here. I'm plugging N1, N2, DO, and R. So this is going to give us 1.52 over DO, which is 12, plus 1 over DI is equal to N2, which is 1, minus N1, which was 1.52, over negative 20. Now, if we do some algebra, we'll get that DI is, let me do this in the calculator, 1 minus 1.52 divided by negative 20 minus 1.52 divided by 12 inversed. We get that DI is equal to negative 9.93 centimeters. Okay. Now, like we said earlier, the sine of DI tells you more about where the image lands. So if we bring our picture, draw a circle again. That's a bad circle. Another bad circle. That's good enough. So this is our circle. What am I doing? Okay, this is our circle. Our defect is here. This distance here is, we said, 12. Okay, this negative sign means that our image has appeared on the side of the refracting surface that we started on. So we started on the left side of the refracting surface, so our DI being negative means that we landed 9.93 centimeters to the left of the refracting surface. If it had been positive, it would have been the other side. We would have been a positive 9.93 centimeters to the right. But since it's negative, we landed 9.93 centimeters on the same side that we started. The negative value just means your image appeared on the same side as you started. So the answer to this problem, if you had to put it in word form, would be the image appears 9.93 centimeters into the sphere, or it could be 9.93 centimeters to the left of the spherical surface. So that would be your acceptable answers. So that's this problem. Let's move on to our next one. So for this problem, we have a similar situation. We have a sphere, but this time our sphere is made of air, and it's submerged inside of a liquid with an index of refraction of 1.4 centimeters. Or not centimeters, sorry. Just 1.4. We're given a diameter of the sphere is 36 centimeters. We're given that the object is 9 centimeters from the refracting surface. And they're given that the index refraction of air is 1. So first thing we want to do is we want to write our equation down. We want to go N1 over dO plus N2 over di. That's equal to N2 minus N1 over plus or minus R. Okay, so now we just, again, we did earlier, we're going to write down the things that we know. We know N1 is the index of refraction where the object starts. In this case, our object starts in air, so it's going to be 1. N2 is the index of refraction where the object ends, or where the light ends, which is liquid, which is going to be 1.4. We know the object is 9 centimeters from the refracting surface. Once again, we don't know di. And we know that the magnitude of R is half the diameter. Our diameter is 36 centimeters here. So half of that is 18 centimeters as our R value. Okay, now what is the sign of R? Well, if we look at our picture over here, let's draw our light ray. Our light ray starts at the object, travels, it encounters a concave surface before continuing on to the liquid. Concave surface means we have a negative R value. So, which means our R value is going to be negative 18 centimeters. The negative because the light hits a concave surface, and the 18 because it's half of the diameter, which is 36. So now that we have these values, we can go ahead and plug in to our equation. So I'm going to say 1.00 over 9 centimeters plus 1.40 over di is equal to 1.40 minus 1 over negative 18. Now once again, a little algebra and some calculator punching, we should get 1.4 minus 1 divided by negative 18 minus 1 divided by 9 divided by 1.4 inverse. We get di is equal to negative 10.5 centimeters. Now, like we discussed on the last problem, what does this mean? The negative sign just means it appears on the same side as it started as. So in our case, if we draw our picture down here, bad circle again. Wow, I'm really bad at drawing circles. Good enough. If our object was 9 centimeters away, our image appeared negative 10, so 10 centimeter or 10.5 centimeters to the left of our surface. Okay, so the worded answer to this problem is the image appears 10.5 centimeters to the left of the refracting surface, or equivalently, the image appears 10.5 centimeters into the sphere. So that would be our answer to this problem. Now, let's move on to our next one. Okay, an object in air is placed 15 centimeters in front of a convex glass surface. The glass has an index of refraction of 1.6, and the radius of curvature of the surface is 25 centimeters. Where's the image located? So now, let's think about this. Let's start our light ray at our object, and let's see what happens to it. So our light ray travels, it hits a spherical refracting surface because it starts in air. This glass surface has an index of refraction of 1.6, which means that they're different, which means this is a separation of the median. It travels into this median, and then at the end, it encounters a rough surface, which means the light kind of goes everywhere. Thinking about this, the only surface we have that's refracting is this first one right here. So that means we're only going to have one index of refraction, or one change in our median. So what we're going to do is we're going to write our equation down. We're going to go N1 over dO plus N2 over di. That's equal to N2 minus N1 over plus or minus R. As per usual, we're going to write down our variables and what we have. So we know N1 is the index of refraction where the object starts. The object starts in air, so this is going to be 1. N2 is where the object, where the light ends. Since it goes crazy at the very back, we're not going to count that. We're going to say just the spherical surface. So it ends in the glass, which has an index of refraction of 1.6. DO is how far it is from the refracting surface, which in our case is 15 centimeters. We don't know DI. Now we know the value of R is 25, but what's the sign? Well, the light leaving our object encounters a convex surface, meaning the center of the circle is on the right side of the surface. So that's a positive value of R. So, keeping that in mind, we bring it over here, we get positive 25 as our R value. Now, like I said earlier, we're going to plug this in. So we get 1 over DO, which is 15, plus 1.60 over DI, which is equal to 1.60 minus 1, all of that over positive 25. Now some calculator punching, and algebra should give us 1.6 minus 1 divided by 25 minus 15 inverse divided by 1.6. That should give us negative 37.5 centimeters. Okay, now let's interpret what our negative sign means. So, the negative sign means the image appears on the same side of the surface that the object started on. So in our picture here, this means that our image appeared 37.5 centimeters to the left of the refracting surface. So that would be our answer to this problem. Our answer to the problem would be the image appears 37.5 centimeters to the left of the refracting surface. That left of the surface is coming from our negative sign that we got here for our DI. If this had been a positive sign, it means it had been 37.5 centimeters to the right of the refracting surface. The negative just means that the image appears on the same side that the object was originally. So that would be our answer to this problem. Now, for our next problem, a bead is embedded inside a glass sphere with an index of refraction of 1.5. The spherical surface facing the observer has a radius of 18 centimeters. The bead is located 10 centimeters from the surface inside the glass. A thin converging lens with a focal length of 12 centimeters is placed 6 centimeters outside the spherical surface. Where is the final image located relative to the lens? Okay, this problem, we want to draw our light wave. Our light wave starts at our beam, or our bead, I should say. It goes, encounters a spherical refracting surface, then the light passes through into air and encounters a lens. And the light goes to the lens. So what we have here is we're transitioning our median here through a refracting surface, and then we're just going through a lens. So let's treat it like that. So initially, our first surface that the light comes in, or our first instrument the light comes in contact to is the refracting surface. So we're going to treat that first. So we're going to do N1 over DO plus N2 over DI is equal to N2 minus N1 over plus or minus R. Okay. Now, like per usual, we're going to label everything we have. So in this case, we have N1 is the index of refraction where the object starts. It starts inside of the glass sphere, so the index of refraction is 1.5. DO is how far it is from the surface, which in this case is 10. Now, N2 is where the light ends up after going through the surface. It ends up in air, so it's going to be, N2 is going to be 1. We don't know DI. And now we know our value of R is 18 centimeters or 180 millimeters. Since we're in centimeters, I'm going to keep going in centimeters. So I'm going to do 18 centimeters. Now is it positive or negative? Well, the light ray leaving the bead encounters a concave surface. So as we said earlier, that's going to be a negative value for R. So now, plugging in all these values to our equation, we get 1.5 over dO, which is 10, plus 1 over di is equal to 1 minus 1.5 over our negative value of r. So the image caused by the refracting surface appears, using math, 1 minus 1.5 divided by 18 minus 1.5 divided by 10 inversed. The image appears negative 8.18 centimeters caused by the refracting surface. So what does that mean? It means the image appeared 8.18 centimeters on the same side as the object. So if we would label that on our diagram, that means our DI caused by the refracting surface is 8.18 centimeters to the left of the refracting surface. Okay, so keeping that in mind, I'm going to erase this work. Remember, the negative just means it appears on the same side that it started as. We started on the left side of the refracting surface, which means our negative value means we're 8.18 centimeters to the left of the refracting surface. Now, as we said earlier, our light ray is now in the air traveling through the lens. So now we just treat this like a thin lens. If you recall, our thin lens equation is 1 over f is equal to 1 over dO plus 1 over di. Okay. Now, what is f? F is going to give us as positive 12 because it's a converging lens. So we get 1 over 12 is equal to 1 over dO. Well, in our case, what is dO? dO is how far the image is from the lens. So we know that the image caused by the first surface is 8.18 centimeters to the left of the refracting surface, which means that image is a total distance of 8.18 plus 6 centimeters away from the lens, which is 14.18 centimeters. So our DO for the lens is 14.18 centimeters. Just to backtrack a little bit and show you why. We care about the image now. The image formed by the refracting surface, it formed 8.18 centimeters to the left, which means its total distance from the lens is 14.18 centimeters. Now, we don't know where the DI, or the image distance, is caused by the converging lens, so we leave that as our unknown. We can solve this, and we should get that DI is equal to 78.1 centimeters. Now, what does this mean? Well, positive signs for DI caused by lenses means that it is to the right of the lens. It means it appears on the same side as the light ray. In our case, the light ray traveled through the lens to the right, so our DI is to the right. So it would be 78.1 centimeters to the right. So the answer to this question in word form would be the image caused by the refracting surface on the lens appears 78.1 centimeters to the right of the lens. And that would be the answer to this problem. Now, our last problem for this video is going to be this one. An object is placed 25 centimeters to the left of a thick glass lens. The lens has a left surface with a radius of curvature of 30 centimeters, while the right surface is flat. The thickness of the lens is 20 centimeters and has an index of refraction of 1.6. Determine the final image location relative to the first surface of this thick lens. So, start normal. Let's draw our light ray. Our light ray starts at the object, travels, encounters this refracting surface, then continues on through the material and encounters this flat surface and then continues on. That's what happens to our light ray. Since it's flat, it just keeps going through. So, this problem, we actually have two separate index or points where we have an index of refraction or an index change, which means we have two separate refracting surfaces. So let's start with the first one. The first one is where the image appeared by the curved surface, because that's where the light hits first. So let's draw our equation. We get N1 over dO plus N2 over dI, and that's equal to N2 minus N1 over plus or minus R. So let's label what we have. So for the first surface, N1, the light starts in air, so N1 is 1. N2 is the glass, that's where the light enters, so it's 1.60. dO is how far it is from the first surface, which is 25 centimeters. Where you don't know what di is, and we know we have an R value of 30, is it positive or negative? Well, the light ray encounters a convex surface, which means it's a positive value for R, meaning that the center of curvature of our refracting surface is on the right side of the surface, not the left. Again, two ways to think about it. So let's write our equation. We get 1 over 25 plus 1.60 over di. That's equal to 1.60 minus 1 over positive 30. So a little bit of algebra and calculator punching, we should get 1.6 minus 1 divided by 30 minus 25 inverse divided by 1.6 inverse. We get a di value of negative 80 centimeters. Now, once again, we need to think, what does the negative mean? The negative means the image caused by the first refracting surface appeared 80 centimeters on the same side as the object was initially. So looking at our diagram up here, this means that our image appeared right here at 80 centimeters to the left of the refracting surface. So let's get rid of this. Now, we have is the light rays are now inside of the glass, and they travel to this second refracting surface. So now we got to do the process again. So now our light is now inside of the glass. So our N1 is now the glass, 1.6. Since the light's inside the glass now, our median 1 for this second surface is inside the glass. N2 is where the light appears. The light goes through that flat surface and appears back into the air. So the N2 is 1. DO now, well, we know that our image is 80 centimeters to the left of the surface, which means its total distance from the flat surface is 100 centimeters. So our DO for the flat surface is 100 centimeters. Okay, we don't know DI. Now, our radius of curvature, this is the flat surface. Flat surfaces, in regard to this radius of curvature, have an infinite radius of curvature. So what does that mean for our equation? Well, let's figure it out. So now let's write our equation out. We get 1.60 over 100 plus 1 over di. Excuse me. And that gives us 1 minus 1.6 over infinity. So what this means, anything divided by infinity, we take that to be 0. So this simplifies down to 1.60 over 100 plus 1 over di is equal to 0. Now, this would give us a little bit of algebra. It gives us a di value equal to 1.6 divided by 100, negative inverse, negative 62.5 centimeters. So, the image caused by the flat refracting surface appears 62.5 centimeters on the same side the light started as. In this case, the light started on the left side of the surface, so that means our image now appeared 62.5 centimeters to the left of the flat surface. Now, if the question asked, where's the final image location relative to the flat surface, that would be the answer. It'd be 62.5 centimeters to the left of the flat surface. In this case, it's asked, well, what's it relative to the first surface of the lens, which is the curved surface? Now, we know that the whole surface is 20 centimeters long. So how far is it compared to the curved part? Well, that would be 62.5 minus 20, which is 42.5 centimeters. So the answer to this problem is the image appears 42.5 centimeters to the left of the first surface. So our answer to this problem would be that. It would be the image, or the final image location, relative to the first surface of the lens is 42.5 centimeters to the left of the lens. And that would be the answer to this problem.